Welcome to This Explainer. Today, we're unraveling a literal 4,000-year-old mathematical mystery. We're talking about a recent breakthrough that takes something notoriously difficult, something that billions of us have struggled with, and makes it beautifully, elegantly simple. So let's jump right into it.
Okay, let's kick things off by acknowledging a bit of shared trauma. Raise your hand if you were ever forced to rote memorize a massively complicated formula just to pass the math test. Yeah, me too. Maybe you even learned to sing it to the tune of Pop Goes the Weasel. You know the one. For most of us, we just plugged in the letters and symbols without actually understanding the underlying math at all. We basically treated it like some kind of dark magic rather than actual logic.
So we all recognize the standard quadratic equation, right? ax squared plus bx plus c equals 0. It's basically just an equation of degree 2. But look, rather than getting totally bogged down in rigid textbook definitions of polynomials, we really need to look at what this equation actually represents out there in the real world.
Which brings us to Section 1, Quadratics in Real Life. This right here brilliantly illustrates exactly why we should care. Take a look at this dynamics calculation for a projectile fired straight up into the air. By using a quadratic equation, specifically 16t squared minus 96t plus 80 equals 0, engineers can pinpoint that this projectile will hit exactly 80 feet in the air at 2 precise moments. It'll hit that mark at exactly 1 second on the way up, and then again at 5 seconds on the way back down. Pretty cool, right?
But this doesn't just apply to rockets. It builds into completely different fields too, like electrical engineering. Here, we use the exact same type of equation to solve for the current in a circuit. By plugging in 20i squared minus 120i plus 100 equals 0, an engineer can figure out that a circuit needs either 1 amp for a 100-volt lamp or 5 amps for a 20-volt lamp. So the math is literally identical, even though the physical reality, rockets versus light bulbs, is completely different.
All right, moving on to Section 2, the shape of math, parabolas.
You know, predicting the shape of these equations is surprisingly simple. Every single time we graph one of these functions, we get this specific U-shaped curve called a parabola. And it always has a single highest or lowest point called the vertex. And here's the trick. If the A coefficient in our equation is positive, the parabola opens upward, giving us a minimum lowest point. But if A is negative, well, it opens downward, giving us a maximum peak, which is exactly like the trajectory of that projectile we just talked about.
So on to Section 3, traditional methods and their limits.
Here's the big question. If these equations are absolutely essential to everything from physics to electrical engineering, why are the traditional methods we learn to solve them so universally frustrating? If you crack open a standard algebra textbook, you'll generally see 3 brute force methods. First up is factoring, which leans heavily on a super frustrating guess and check process. Second is the standard quadratic formula, which, as we discussed, requires blind memorization without any real logical understanding. And third is completing the square. This involves adding and subtracting highly specific fractions to force a perfect square. It is conceptually cumbersome and just incredibly difficult for beginners to wrap their heads around. Every single one of these introduces totally unnecessary friction into learning.
Furthermore, things get incredibly messy when reality doesn't cooperate with our math. For instance, when engineers try to use the traditional formula to find when that exact same projectile reaches 160 feet in the air, the formula spits out complex imaginary numbers, specifically 3 plus or minus j. Physically, this translates to the fascinating reality that the object simply never reaches that height. It just doesn't go that high. But computationally, those imaginary numbers completely derail the basic guess and check factoring methods we're usually taught.
Which leads us perfectly into Section 4, a revolutionary simple method.
Enter Carnegie Mellon mathematician Po-Shen Loh. In 2019, he published an incredibly elegant, simple proof that completely bypasses the rote memorization of the traditional formula. Instead, it relies on basic logic you already know. Think about it. If you're looking for 2 numbers that sum to negative b, they absolutely must have an average of negative b divided by 2, right? That means the 2 roots are just that average plus or minus some unknown offset, which we'll just call z. And when you multiply those 2 roots together, it yields a super simple difference of squares that must equal the product, c. Okay, I know that might sound a little abstract, so let's look at exactly how beautifully this works in practice.
Let's apply it directly to a real example. X squared minus 2x plus 4 equals 0. Since the sum of our roots is 2, the average of that sum is simply 1. So we set up our offset equation. 1 minus z times 1 plus z equals our product, which is 4. That expands super easily to 1 minus z squared equals 4.
Using just basic math, we immediately see that z squared is -3, meaning z is the imaginary number I times the square root of 3. So our roots are 1 plus or minus I root 3. Boom. It proves that irrational and complex numbers pose absolutely no obstacle here. There's no guessing, no massive formulas to sing and memorize, just pure, straightforward logic.
Finally, Section 5, a 4,000-year-old mystery.
Now this brings us to a genuinely mind-boggling realization. How did a method this mathematically natural fly under the radar for 4 millennia? Because the pieces for this breakthrough were actually scattered all across history. If we look back in time, the Babylonians understood the sum-product substitution over 4,000 years ago using tables of squares. Then, around 250 AD, the Greek mathematician Diophantus utilized average parameterizations. And around 825 AD, the Persian mathematician Al-Khwarizmi solved quadratics abstractly. They all had a piece of the puzzle, yet these brilliant early mathematicians lacked the concept of complex numbers to combine these insights backward into Luh's completely universal method.
Low himself notes that he stumbled upon this fusion of Renaissance-era math and Babylonian tricks simply by trying to create alternative, elementary explanations for middle schoolers. Let that sink in. By trying to teach the absolute basics, he unlocked a 4,000-year-old door. As he wrote, more surprises certainly await the light of discovery. It really proves that returning to the fundamentals with fresh eyes can yield absolutely incredible breakthroughs.
Which leaves us with this final, provocative thought for today's explainer. If a concept as universal as the quadratic formula, literally something memorized by billions of people worldwide, could harbor a wildly simpler solution that went unnoticed for 4,000 years, what other established rules in your daily life are just waiting for you to look at them from a fresh, curious angle? Stay curious, keep questioning the formulas you're handed, and thanks so much for learning with me today.